Hello, fam. This is Zaz from Entertainment, reminding you that enthusiasm implies excellence. We are still doing our number pattern under the subtopic geometric sequencing. What is geometric sequencing? A geometric sequence is a sequence of non-zero numbers where each term after the first is found by multiplying the previous one by a fixed non-zero number called the common ratio. So this is our general term for a geometric sequence. Okay, for us to find the pattern of the sequence, we have to have at least first four terms so that we can follow their pattern. So here we have term number 1, of which is AR to the power of 1 minus 1, because this one represents n. So whenever I see n, I plug 1 here, of which is equal to AR to the power of 0. Any number with an exponent of 0 is equal to 1. So we end up having A. This is our first term. Moving to our second term. Our second term will have AR. Now when I see n, I replace n with 2 minus 1. So this one becomes AR. This is my term number 2. Moving to term number 3. We have AR to the power of 3 minus 1. So my term number 3 becomes AR to the power of 2. Term number 4 is equal to AR. When I see n, I replace it with 4 minus 1, of which is AR to the power of 3. That one is term number 4. Now I have my sequencing. My sequence starts from 1 to 4, from term number 1 to term number 4. My term number 1, my term number 2, my term number 3, my term number 4, of which is AR squared, AR to the power of 3. Okay, following the definition, if the definition says that a quadratic sequence is a sequence of non-zero numbers where each term after the first term is found by multiplying the previous one by a fixed non-zero number called the common ratio. So let me underline this line. It's found by what? By multiplying the previous one by a fixed non-zero number. That number is called a common difference. Where do we start? We start after the first term is found. Okay. So here, if you can pay attention and follow me, I have my first term. Okay. And then I have my first term multiplied by R. Moving to my third term, I have my first term multiplied by R multiplied by R. My third term, my fourth term, I have A multiplied by R multiplied by R multiplied by R. So if you can follow this path, from my first term to my second term, I multiplied by R. From my second term to my third term, I multiplied by R. But when I relate my third term and my first term, that means I multiplied by 2 R's. So it's R from term number 1 to term number 2 and R from term number 2 to term number 3. And moving from term number 3 to term number 4, I also add another multiplication of R. So I end up having these 3 R. So R times R times R, same base, adding exponent. That's why I have my R cube. Okay, so how can I find this common ratio? This common ratio is R But another easy way of finding this R, you can just simply say term number 4 over term number 3 equal to the term number 3 over term number 2. In fact, not equal to, but it should be equal to for you to conclude and say this is a geometric sequence. So if it's not, that means that one is not a geometric sequence. It should be, you understand? So let us assume that it is equal, because here we know that we are dealing with geometric sequence. So if we deal with geometric sequence, automatically I now know that their ratios should be equal. So my term number 3 over term number 2 okay, let me not use this space, let me add space. So my term number 4, my term number 4 over term number 3, term number 4 is AR to the power of 3 over term number 3 is AR to the power of 2. It should be equal to term number 3 over term number 2. Which is AR. And it should also be equal to my term number 2 over my term number 1. So here you see that you have same basis. The only thing you subtract the exponent, you end up having, let me show you, okay, this one and this one. So you have same base, you subtract the exponent, so you end up having r to the power of 3 minus 2, of which is equal to r. Here you end up having, because this and this cancels, end up having r to the power of 2 minus 1, which is equal to r. Here you see this and this cancels, you end up having r over 1, which is equal to r. So you can see that my ratio now is common. So r is common ratio. Okay. So this is how I find my common ratio. That means these numbers are keeping on incrementing using same ratio or equal ratio. Okay. Let us have a look at this example. Here you are given a sequence of 2, 4, 8, 16, 32, and 64. But they never mention of which sequence does this sequence lies on. Is it an arithmetic sequence, quadratic sequence, or a geometric sequence? So since I'm dealing with geometric sequence, let me start with geometric sequence. I have to check features of geometric sequence, and then I can conclude and say this is a geometric sequence. But if features of geometric sequence are not being satisfied by this sequence, that means this is not a geometric sequence. What is it that I know from my geometric sequence? My geometric sequence tells me that when I divide term number, let me use these first three terms, term number 1, term number 2, and term number 3. Term number 4, 5, 6. Now let me ignore them at the moment because I want to make my workings to be much more simpler than it will be if I keep on finding this ratio, So term number 3 over term number 2. I won't equate it because no one told me that this is geometric sequence. I will start by finding these sequences independently. So here, my term number 3 is 8 and my term number 2 is 4. I get the value of 2. Okay, let me now move to my term number 2 over my term number 1. So my term number 2 is 4 over 2. I still get 2. Now I can conclude and say my term number 3 over my term number 2 is equal to my term number 2 over my term number 1, of which is r. Therefore, my r is equal to 2. Okay. I'm required to determine the general term, but before determining the general term, I have to know the sequence that I'm working with, because no one told me that this is a geometric sequence. I was just given a sequence, a random sequence, and then I have to perform my working and relate my working to the features of the sequence that I supposed to find general term for. So in other words, now since I know that I do have a common ratio here, let me now write my general term for a geometric sequence, of which is Tn is equal to ar to the power of n minus 1. Luckily, I now know my r. And one more thing, you see that on your sequence, you do have your first term. We said our first term, of which is T1. You can also write your first term as A, or our first term is also denoted by A. So my A here is 2. So I have my A2, I have my R2, meaning I can write my general term to be 2 times 2 to the power of n minus 1. Okay. Here I have one term, but these two terms, I cannot add them, I cannot multiply them, because they are two different independent terms. The only thing I can use here, luckily, I have 2 and 2, and they multiply one another, so they have same base. The only thing that I can do, I can add their exponent. So my Tn here will be 2 to the power of n minus 1 plus 1, of which is my Tn is equal to 2 to the power of n. You cannot, let me emphasize this, good people. I want to write it in red so that you note the danger. Do not say Tn is equal to, when you see 2 times 2 to the power of n, you cannot say 2 times 2 to the power of n minus 1 is same as 4 to the power of n minus 1. This is totally unacceptable. Yeah, this one is unacceptable. So when it's like this, you leave it like this. But just because you see that bases are the same, that's where you can perform your laws of exponent. But if here it was 3 times, let me not write times, but let me leave it as a dot. 3 times 2 to the power of n minus 1. You cannot say this is 6 to the power of n minus 1. No, this one is completely wrong. But you leave it as it is. This is your general term. But here, this is our general term. Moving to my next question. My second question says, which term in the sequence is 1024? Okay. The fact that they want to know which term, and let me highlight this part, which term. Okay. Now I know that I need to know my value of n. This is the value, and that value is denoted by Tn. So here I'm required to find my n. So for me to find my n, I have to use my general term. My general term says my Tn is equal to ar to the power of n minus 1. But luckily, on my previous working, I did work out my general term. So my general term is Tn is equal to 2 to the power of n. So my Tn is 1024 is equal to 2 to the power of n. Okay. We normally know that when we have two powers, we equate two powers of same bases, you just drop their base, then you equate their exponent. But here, since we have 1024 as a huge number, it makes things difficult for us to write 1024 in terms of 2 to the power of something. You understand? So that is why I just decided to go and borrow this logs function. I introduce my logs function, introduce my log on my left hand side and on my right hand side. So as the result, I have log of 1024 being equal to, when you introduce a log multiplying a power, you end up having an exponent log base. So here I can divide by log 2 because I want to make my n a subject of the formula log 2. So my n is equal to, let me go and take my famous calculator. Where is my famous calculator? My famous calculator. Okay, here is my famous calculator. So here you can see that I have log of 1024 all over log of 2. My answer is 10. So this is my solution for this problem. Okay. You know that, guys, I can't leave you alone. I want to keep you practicing so that you can get used to what we've just did from my lesson. So yeah, this is just to try. You are given the geometric sequence. Lucky you are. You are told that this sequence is a geometric sequence of 320, 160, 84, and 40 up to infinite. And we are required to determine the general term of the sequencing. And your second question is, which term in the sequence is 5? Guys, I hope you will enjoy doing this exercise. Thank you. I'm looking forward to see you in my next lesson.